Now, one last topic of discussion that remains in the analysis of the second variation is that what are the saddle points. See, we have touched upon the topic of the extrema being maxima or minima, but how about an extrema being a saddle points. So, what is the criteria of detecting saddle points? The answer lies in extending our Morse lemma from the finite dimensional to the infinite dimensional case, namely the solution lies in determining what is the Morse index for the infinite dimensional function space. Okay. So, let us look at the saddle points. Okay. So, which means the presence of conjugate points implies that the functional j neither so this is a statement we mentioned few minutes back. The presence of conjugate points guarantees that the functional neither has maxima nor has minima, right. Okay. So, this question is there a way to classify the functional with conjugate points corresponding to the one that we have done for saddle points in finite dimensional case. Okay. Is it possible to classify extremals with conjugate points? Is it possible to classify extremals with conjugate points in a manner similar to the finite dimensional case for saddle points, right. What did we do for saddle points, finite dimensional case for saddle points? We looked at the Morse lemma and we calculated the Morse index. If the index is not one of the extremes, that is lambda equal to n or 0 in the finite dimensional case, then we are guaranteed to have saddle points, right. But how about the infinite dimensional case? What should we do for those cases? So, recall let us recall the Morse lemma. Recall Morse lemma for the finite dimensional case, right. Note that Morse lemma used to count the number of negative signs in the canonical representation of f around a given point x naught. Okay. So, what did Morse lemma used to do? We were counting, it counts the number of negative signs in the canonical representation of f near the point x naught. Okay. So, in the infinite dimensional case, let us look at what happens to the Morse lemma. So, in the infinite dimensional case, let me denote y to be an extremal for j. So, let y be an extremal of the functional j, and let us also denote a vector space on which these functions are defined. Let me call this vector space or the Hilbert space as H. So, let y be an extremal for j, and let us define my second variation del square j from the Hilbert space H cross H to R be the second variation. Okay. So, which means that the Morse index of the extremal j is going to be the maximum subspace in which the second variation is negative definite. Remember, the Morse index always used to count the number of negative signs in the finite dimensional case. So, in the infinite dimensional case, it gives us an idea of the maximum subspace where the second variation is going to be negative definite. Okay. So, so let me write down what I just said. So, it implies that the Morse index is the extremal, the Morse index is the extremal y of j. The Morse index of the extremal y of j is the maximal dimension, of the subspace H on which the second variation is negative definite. Okay. So, that is what the infinite dimensional equivalent of Morse index tells us. Okay. There is one more issue that I need to mention, that is regarding the multiplicity of the conjugate points. So, again recall, what are conjugate points? Conjugate points are roots of our solution to the Jacobi accessory equation. Now, we also know that the Jacobi accessory equation is a second order differential equation, which means that the maximal number of linearly independent solution to that equation will be 2, or it implies that for any non trivial conjugate points, the multiplicity of the conjugate points cannot exceed 2, right. So, let me write down what I just said. Multiplicity of kappa, which is conjugate to x naught. Okay. So, this is the number of linearly independent solution, u to the Jacobi accessory equation, right, which satisfying u of x naught is equal to u of x 1, u of kappa is equal to 0, right, where my point kappa is not equal to x naught. Okay. So, that is the multiplicity. As I said, the multiplicity cannot exceed 2 because the Jacobi accessory equation is of order 2, right. So, since the equation is a second order ODE, it must have the multiplicity cannot exceed 2. Multiplicity of a conjugate point, right, kappa under consideration cannot exceed 2. Okay. So, we are ready to discuss the major result by Morse for infinite dimensional case. So, the result is as follows. So, this is described in the form of a theorem, or the Morse index theorem for infinite dimensional case. Morse index theorem for the infinite dimension function space. Okay. So, the theorem says that suppose y is an extremal and lambda be an index for the second variation of j, then lambda is going to and suppose the number of points which are conjugate to point x naught, the starting point, are finite, then this number of points which are conjugates are nothing but the Morse index lambda. Okay. So, what the result says is, suppose y be an extremal, y be an extremal for the functional j, and then the index lambda of the second variation del square j is equal to the number of points in x naught x 1 conjugate to x naught, number of points in x naught x 1 conjugate to x naught, and this index is finite. This index is finite. Let me highlight the importance of this result with a quick example. Recall our example, recall j of y given by integral 0 to L y prime square minus y square dx, and this time I am going to assume that L is, let us say 3.5 pi. Okay. So, certainly it is bigger than pi. Now, note that the solution to the Jacobi accessory equation, one of the solution is u 1, which is sine of x, and we saw that for this solution the point kappa equal to pi as well as 2 pi as well as 3 pi, they are all conjugate to the point x naught, which is 0, right. So, the conclusion here is that the Morse index for this function space is 3, right, and so that tells me the maximum dimension of the subspace where the second variation is negative definite. Okay. So, which means that my Morse index lambda here is 3. Okay. So, that is how we use this theorem for by Morse in the infinite dimensional function space. Okay. So, certainly if the Morse index is 0, we are guaranteed to get a minima, and if the Morse index is n, well, infinity in our case, then we are guaranteed to get maxima, but that will not be the case because of this statement. Okay. So, the Morse index guarantees the existence of either saddle points or the local minima. Okay. So, then I am going to talk about a specific class of functionals. This is the last topic on the theory of calculus of variations, namely the case where our integrands in the functional are convex, or they are of certain characteristics or convex integrands. We will see that the extremals that we get for these class of functions are local minima or minima. Okay. So, what I just said is we are now going to focus our attention on convex integrands to the functional convex integrands. Let me call this as Ci. Okay. So, as I just said, for convex integrands there is a sufficient condition for a minimum, there is a sufficient condition for a minimum not involving conjugate points, essentially the extremal will be a minimum for convex integrands. Okay. So, let me just revise the basics of convex functions, convex sets from our finite dimensional case. Let us do that. So, let us look at let us start our revision in Rn or finite dimensional case. So, convex functions. So, let us revise convex functions in Rn. Okay. So, we see that a set is convex, a set omega, we are going to restrict our attention only to R2, and similar ideas are extended to R3, R4 and so on, higher dimensions. Okay. So, let us start with a set which is a subset in R2, and it is said to be convex if a line segment between any two points in a set also lies in the set. If a line segment between 2 points, Z1 and Z2 lying in omega, also between 2 points Z1 and Z2 in omega also lies in the same set omega, right. So, what I just said is the following: if the point Z1 and Z2 is in omega, then I have the condition that 1 minus t times Z1 plus t times Z2 is also in omega, okay, for all t in 0 to 1. Okay. So, let me call this line segment by omega of t, right. So, it is easy to see some of the convex sets are R2 itself, or let us say a set which is described by the interior of a unit circle, or a set where we have that the absolute value of the components are positive and so on so forth. There are several, it is easy to construct convex sets. So, example is we have the sets R2 itself, the entire 2D plane, or the sets described by the following two tuples y comma omega, such that y square plus omega square is inside a disk of radius 1, or a set y comma omega. So, these are all in R2, y comma omega in R2, such that they are bounded above by 1. So, these are some of the examples which are all convex. Okay. So, these are my convex sets. Okay. So, then I describe what are convex functions. So, that is my convex set. So, a function f from omega to R2 is convex if f of omega of t, which is given by well. So, these are my, so omega itself is a vector. So, this is my omega. So, f of omega of t, which is given by f of 1 minus t times Z1 plus t times Z2. This is also this is less than or equal to 1 minus t times f of Z1 plus t times f of Z2, okay, essentially the triangle inequality. So, as long as this function satisfies this inequality, we call this function to be a convex function in Rn in general, but right now we are showing the result in R2. Okay. So, then we can use certain results, for example, the mean value theorem to arrive at certain other relations. So, let me start numbering some of these relations here. So, let me call this relation as R1. So, I am going to use some of these relations, and then I am going to use the so called mean value theorem. So, using mean value theorem, let me say that the mean value theorem says that there exists, for convex function there exists a number tau from 0 to t, the interval under consideration, such that such that f of omega of t is equal to f of z 1 plus t times z 2 minus z 1 times grad of f of tau, right, f of omega tau. Okay. So, this is a vector dot product because we are talking about vectors, and let me call this result as R 2, right. So, the inequality in R 1, the inequality in R 1 has been changed to an equality in R 2 using the mean value theorem. Okay. So, let me rewrite this condition R 2. So, what we have is there is one small observation that I want to make. Notice that since my functions f and grad f are smooth, that is the derivatives are continuous and the function itself is continuous, then it implies and my variable tau is between 0 to t, it implies that this particular limit t going to 0 of grad of f of omega bar of tau, right. So, we can nicely take the limit inside the function or inside the gradient operator. We will see that this is also equal to grad of f of z 1, okay, because recall that omega bar of tau is z 1 plus tau times z 2 minus z 1. So, that was what my straight line omega bar tau was. Okay. So, in the limit my gradient reduces to the following. So, then let me call this relation as R 3, and I am going to use R 3 in R 2 to arrive at the following. Well, in fact, R 3 I am going to use R 3 in R 1, the inequality. So, using R 3 in R 1, the inequality, I arrive at the following relation z 2 minus z 1 dot product with the grad of f of z 1 is less than equal to f of z 2 minus f of z 1. Now, this particular result, let me call this as well. So, what I have is, yeah. So, let me call this as my result R 4. Okay. So, from R 4 further if we assume, so we are talking about the functions in finite dimensional space in R 2, and we know that a point z is a critical point provided the gradient vanishes. So, suppose z 1 is a critical point. So, suppose z 1 is a critical point, or I am saying that the gradient of the function at z 1 vanishes, then I see that f of z 1 is less than f of z 2, right. This is from my condition R 4, and or otherwise the point z 1 is the local minimum, It is always going to be the minimum compared with the function values at other points in its neighborhood. Okay. So, which means that any extremal for a convex function will be a local minimum. Okay. We can extend this same idea for our functional optimization, where our integrands of the functional are convex functions. Okay. So, let us continue the extension of this finite dimensional case to the functional case. So, let me consider my functional, which is a basic fixed point functional x 0 to x 1 f of x y y prime dx, and let me again start with a convex set in which the domain of the integrand is defined. So, suppose omega of x, which is given by the tuple y prime y and y prime is in R 2 such that x comma y prime is in the domain of f. This 3 tuple is in the domain of f. This is my domain of f such that, so this set is convex, right, and further f from omega x to we are describing it in R, the function is the integrand function. So, f from omega x to R is also convex. So, this is our starting assumption, right. If that is the case, we can quickly use some of the results that we have shown in the finite dimensional case, namely the result R 1 to R 4. So, I am going to use the result R 4 here. Okay. So, using, so which means for any point points y comma y prime, and let us say the perturbation of this point y hat comma y hat prime prime in omega x, it implies R 4 means that I have the following inequality by R 4 I have the following inequality, that f of x comma y hat prime minus f of x comma y hat, well y comma y prime is greater than or equal to y hat minus y times, I am just using the result R 4. So, where one of them is z 1, the other one is z 2, y hat times the gradient of f of y plus y hat prime minus y prime times the gradient of f with respect to y prime. Okay. Okay. So, essentially I have used the chain rule. So, this result follows from the chain rule. Okay. So, that is the gradient. Well, essentially my gradient is the derivative with respect to y comma the derivative with respect to y prime. So, that is my 2 dimensional gradient operator. So, that is how we are getting this result, and from here so which means that my difference of the perturbed functional minus the original functional, right, is the following. It is going to be the integral from x 0 to x 1 f of x of y comma y hat prime dx minus integral well let me also say that, let me keep everything under my integration curve, this dx, we see that this is also going to be greater than or equal to, via the inequality above, this is greater than or equal to integral from x 0 to x 1 y hat minus y times f of y plus y hat prime minus y prime times f of y prime, okay, dx. Okay. Now, then the next step involves, we are going to assume that y is an extremal or it is the solution to the Euler Lagrange equation. So, let me say that suppose y in S is an extremal and y hat also in S is the perturbation of y, right. I see that the moment y is an extremal, first of all we can take we can reduce this second quantity by integration by parts. So, let me do integration by parts, and I see that the right hand side of this inequality reduces to well, it reduces to y hat minus y times f of y prime evaluated at x naught to x 1 minus the integral, well let me take it plus, so that we can club everything together, x naught to x 1 y hat minus y times f of y minus d dx of f of y prime dx. Okay. So, now it turns out that since y and y hat both lie in S, so it must satisfy the endpoint conditions, right. So, this means that y at x naught is equal to y hat at x naught, and y at x 1 is equal to y hat at x 1. So, that is the endpoint condition that it must satisfy, or this difference will be 0. And similarly, we see that since y is an extremal, then it leads to the condition that the solution to this equation inside the bracket, which is the Euler-Lagrange equation, will be 0. So, what have we found? We have found that the variation, the difference j of y hat minus j of y is greater than equal to 0, or I have that j of y is less than j of y hat, or I see that the extremal y is a local, it is a local minimum of j. Okay. So, that is the conclusion that we can right away derive from our finite dimensional case. So, the analysis becomes very easy when we are dealing with convex integrands. In after few minutes, I am going to introduce a topic in optimal controls, where we are exactly going to discuss convex integrands. So, let us wrap up this section by providing some results in the form of theorems and give some examples on how to solve optimization for convex integrands. So, I have two theorems or two results to discuss. The first says that how to describe, how to find the minima for functionals with convex integration. The answer lies in just finding the extrema of the functional, which is going to be the minima. So, it says the following: suppose for each point x in x naught to x 1, the set omega x is convex, the set omega x is convex, and suppose f is also a convex function, the f is a convex function of the points y comma y prime in omega x, if y is a smooth extremal, y is a smooth extremal of j, then j has a minimum at y, for this is the statement for fixed endpoint problems, Okay. So, that is quite obvious through our analysis few minutes back. And then the second result in the form of another theorem tells us how to find, how to check whether the function is convex or not. So, the second result says, suppose omega subset of R 2 be a convex set, and f from omega to R has continuous first and second partial derivatives, then I have that f is convex if and only if for all points y comma omega in this set omega, I have that f of y y at y comma omega is non-negative, f of omega omega at this point is also non-negative, f and this discriminant f of y y, f of omega omega minus f of y omega or omega y does not matter, this is also non negative, right. We call this expression by delta. Okay. So, let me wrap up this discussion by looking at few examples. We are going to revisit our examples of the geodesics on a plane. So, let us consider the geodesic example on a plane. So, my j is my arc length integral in this case. So, 1 plus y prime square dx, and if I were to find out, first of all we have to check whether the integrand is convex or not, then only we can conclude something. So, which means my integrand f is square root of 1 plus y prime square, and we see that f of y y is equal to f of y y prime is equal to 0, and f of y prime is 1 by 1 plus y prime square to the power 3 by 2, and of course, this will be greater than 0 for any value of the derivative y prime. We can see that it certainly, these conditions certainly satisfy my convexity conditions. It implies that so satisfies the conditions of theorem 30. So, it implies that f is convex. The result from this statement that f is convex implies that the extremal that we find, which is the straight lines, will be local minima. Okay. So, from theorem 29, the previous one, I can see that y equal to mx plus c, which is the solution to the Euler Lagrange equation are curves of shortest arc length, okay, or they are the minimal solution or the minimal extremal to the functional j. Okay, let us look at one or two more examples. Another example that I have is that of the catenary. So, catenary. So, let me take, so in this case my integrand is of the form y times 1 plus y prime square, and let me calculate the various derivatives. So, f of y y is 0, f of y y prime is y prime by square root 1 plus y prime square, and I see that in this case it does not matter whatever is f of y prime, but my discriminant delta comes out to be negative, right, negative if my y prime is non-zero, right. The moment we have non-zero slope, the discriminant is negative, which means that f is not convex, or we have seen that one of the extremals that we find for the catenary problem does not give either a minima or a maxima, right. So, in our note from our previous lecture, we saw that we found in fact we found conjugate points for the extremal, guaranteeing the extremal being not being a minima or a maxima for the extremal. Okay. And then finally, here is one more quick example. This example, I consider the function, the integrand of this form, which is c1 times y minus y prime minus c2 whole square. So, I can check where my c1 and c2 are constants. C1 and C2 are constants. Let me take my subset of f to be R square. So, I know that the subset is convex. I have to check whether f is convex or not. notice that f of y y after differentiating twice comes out to be 2 c 1 square. So, this is always non-negative, and the quantity f of y prime is coming out to be 2, which is positive, and f of y prime comes out to be negative 2 c 1, which comes again which is non-zero, right. Okay. So, we will take that both are not 0. So, C 1 and C 2 are constant such that both are non-zero. So, then we have a strict inequality. From all these derivatives I can conclude that my discriminant delta is 0, but f of y y and f of y prime they are all positive, implying that f is convex. Okay. And further, f is convex or the extremal due to the fixed point problem with this as this quantity f as the integrand is guaranteed to give me a minimal solution, right. So, this is from theorem result 30, and from result 29 I can conclude that the extremal of the fixed point problem given by j of y is equal to integral x naught to x 1 f of d is a minima. Okay. So, that is how we typically solve problems with convex integrands. Now, let me now focus. So, that concludes my discussion on all about the theory of calculus of variations.